Hey there, and welcome to this next lesson of higher mathematics. We're looking at geometry now. So the first lesson on geometry, we're just looking at two-dimensional shapes. So this should be a reasonably easy going lesson, hopefully. So we've got a few things to be looking at though. So we're going to look at the very beginning, distances and angles. How do we measure distances and angles? Make sure we've got those basics down. Triangles and quadrilaterals. Okay, these are our most basic shapes that we can often build many other shapes from. Then we're going to look at polygons, which is a general name for uh, a shape with any number of sides, but just straight sides. We're not looking at any curved sides yet until we get to circles. So, circle is a circle. We're looking at the properties of what a circle has, what we need to be aware of. Then we're going to be looking at perimeter and area, what these terms are, how do we calculate them for various shapes, whether regular shapes or more irregular shapes. So here we go, distances and angles. So a lot of this should be relatively straightforward. So we should be able to get through this quite quick. So length, a distance, we can refer to that by various names, length, width, and depth, depending on the context and what we're talking about. Um, we this can be curved, but the shortest distance between 2 points is always going to be a straight line. So we take 2 points like this. We could take any line between them, but the shortest is always going to be the straight line. So that's a key property to always be aware of. And we have a variety of units we can use to measure lengths. Typically, we use meters or centimeters, metric units, but we can also use imperial units as well, but that would be less common. So distance is pretty straightforward. Angles a little bit different. So angles are a measure of rotation, essentially. So, and we only have one measure that we use at GCSE level, which is degrees. So if we have two lines like this and we have a point, we imagine, rotating from one line to the other, like imagine that's like a hinge. And so that would then be our angle. And how do we measure that? So a full rotation we measure as 360 degrees, which is just what mathematicians have essentially agreed it would be, because 360 is just a highly divisible number. So we can divide up a circle into many different ways and avoid essentially getting decimal numbers. Uh, let's say it's integers. So if we wanted to measure an angle like that, you have this what's known as a protractor. We line up the zero with one line, and then we can measure around to the other line, and we see we get 40 degrees. Imagine that's all pretty straightforward. 40 degrees for that angle. Okay, so what does that mean as like a proportion? So just like how we have, say, a percentage, say 15% is 15 out of 100. And so that's an easy way to convert a percentage into a fraction. We have a similar thing with degrees, like 40 degrees is basically 40 out of a total of 360. So this tells us that this kind of slice we've got here is essentially 1/9 of a full circle. So that's a very important property to be aware of. And we're going to be needing that later when it comes to looking at things like sectors, segments, arcs, if you're familiar with what those things are. So we can see angles can also be used for other things. So it's not just like the angle between two lines like what we're seeing there, but it could also be used to measure orientation, like say a square like this. If I was to rotate 45 degrees, that, we can use rotation angles for that. Or we could do measuring a rotation about a point, like kind of like orbiting around a point. That point would be then our center of rotation. And this square, you could imagine rotating that round 90 degrees around that point. That would be another example. So yeah, so we often use it as what is essentially like a transformation, rotating something or essentially moving something like that. We'll be looking at those more later in our geometry lessons. So, uh, got to be aware of different names of particular angles. We have right angle, straight angle, and complete angle, which are these ones here you might have seen dotted around. So these are specific angles. Right angle being exactly like this box corner, straight angle being the angle on a straight line, and then full rotation being, the full circle. Uh, and then we have names for angles that are ranging in between. So we've got here acute angle being 0 to 90, obtuse being between the 90 and 180, and then reflex being between 180 and 360. So you want to be aware of those words. So a lot of these are key words that I've mentioned throughout this section here. You want to be aware of because I'll be using them throughout and yeah, you'll need to know what they mean. So let's move on to triangles and quadrilaterals. So various different shapes we have. Triangle, any shape with three straight sides. We have different types, different properties. First of all, the equilateral triangle, where all the sides are equal and all the angles are equal. And so we know what that's going to be because all the angles in a triangle add up to 180. So each angle individually is going to be 60 degrees. We'll see later like where that essentially comes from, like how we know all the angles add up to 180. We've got isosceles triangle, which is one like this, where we have two equal sides, which we can denote by a little line across them, showing that they're equal. That makes then the two angles at the bottom equal. And say if we knew that that angle at the top was 40 degrees, we can then use that to calculate the other two because we know they all add up to 180. If I take away 40 from 180 and then divide that by 2 because the two at the bottom are equal, we get 70. Vice versa, if I knew what that that bottom angle was 30 and was instead trying to calculate the angle at the top, well, I can do 180 minus 2 lots of the 70, and then what's left over will be the one angle at the top. So using that fact that the two at the bottom are equal, if as long as we know one angle, we can work out the other two. All other triangles are scaling. So something like this, where all the sides can be different, all the angles can be different, and we need some other information really to be able to work out anything. So those are our keywords describing triangles. Isosceles tends to be the one we come across most often. So a quadrilateral, four-sided shape. We have many different types of quadrilaterals. We've got to be aware of some of the common names. So here we have square, four equal sides, four equal angles. Rectangle with four equal angles, but only the opposite sides are equal. And then we have rhombus and parallelogram, which are closely related to these. So a rhombus is basically like a square that's been stretched or squashed somewhat, and you see the sides are the same, but the angles have changed slightly, and only opposite angles are now equal to one another. A parallelogram is like a rectangle, but again slanted, and so you have opposite angles are the same, but uh, the opposite sides are still the same as well, just like the rectangle. Finally, we have the trapezium, one we tend to come across more often in high level math, where it's got similar properties where we have equal angles like this, and instead of being slanted in the same direction like a parallelogram, there you've got two sides slanted inwards. So those are our common types of shapes, and because they're common, they tend to have actual names, and so we names that we've attributed to them. So you've got to be aware of what those names are. So if you have a question that says, "Oh, it's talking about a rhombus," you then know straight away what it's talking about. So now we're looking at polygons, which is a general name for a shape made up of straight sides. So in general, yeah, polygon with straight sides. Many polygons have unique names, depend on the number of sides it has. We only need to be familiar with the ones up to 10, really, or maybe 12. Like you've got 11 sided shape, and we have perhaps a 12-sided shape, which is a dodecagon. But yeah, only really up to 10 is what we need to know. And see, we've got the names here. And the prefixes at the start of each name are important to be aware of, like pen, hex, hep, oct. These things, mean essentially 5, 6, 7, 8. Like oct is like octopus having 8 legs, or hex. You might have heard of in many contexts. Essentially related to 6. So if you're familiar with those words, because you might see them in other places, and it's good to know. So straight away you know it's to do with this particular number. So most of the time we're interested in regular polygons, which is where all the sides and angles are equal. So here's an example of all our different polygons. 5, 6, 7, 8, 10, 12 sides, and you might notice that as you take more and more sides, it starts to become more circular. And if you actually go to essentially like an infinite number of sides, it actually converges towards a circle. And that's actually how we deduce the formula for the circumference of a circle. But I'm getting a bit ahead of myself there. We've got a bit of information out on the bonus material, though, if you're interested in where the formula for the circumference of a circle comes from. So now let's look at interior and exterior angles of a polygon. So this is what we tend to be interested in. So because there's relationships between them, and so by having information on one, we can use that to find information on the other. So far we've considered interior angles, but we also have exterior angles. So say if we take a shape like this, which you should recognize as a heptagon because it's got 7 sides, and it's a regular heptagon, all the sides are equal, so that means all the interior angles are equal. But we also have exterior angles, which we can draw by extending out each line like this as we go round. Like I'm just looking around anti-clockwise, and these angles here that are on the outside count as exterior angles. Hence why they're called exterior, because they're on the outside. And you might notice that together, an interior angle and an exterior angle make a straight angle, so they add up to 180. And okay, say if we was trying to find out what these interior angles or exterior angles are, like can we work out what they are from this information alone? And it turns out we can. And the way you want to think about it, like sometimes people can remember formulas. I've never really memorized formulas for this. Like you can work this out completely intuitively. If you think like, okay, if I've labeled A there being just for, one exterior angle is A. And I'd imagine myself, like imagining a vehicle at a particular point here, and I'm going to drive around the shape. So I go along the first side, and now I turn to go down the next side. So I've turned that angle A. Now I continue round and I turn the angle again. So now I've got A plus A is how much I've rotated. Now I go round to the next point and I'm rotating again. So I've now rotated A plus A plus A. And I continue this all the way around the shape until I get all the way back to the start at the same orientation again. And you notice you would have just turned 7 times. So I'm going to have a total of 7A. 7 lots of exterior angles, obviously, as I've gone round. Because that's the angle that I've turned at each point, isn't it? It's the exterior angle is what I've turned. But notice what I did there was just a full loop. I did 360 degrees. So therefore, 7 times the exterior angle here must equal to 360. And you'll get the same for any other shape. Like if it was a hexagon, it would be 6 lots of the exterior angle add up to 360. Or for a decagon, it would be 10 lots of the exterior angle add up to 360. And so basically the number of sides or number of points times by the exterior angle is going to equal 360. And so now we've got a simple little equation. We just divide by 7. We then get what that exterior angle is, which in this case is a decimal, but many times it won't be because 360 is so divisible. And then once we've got that, because we know the interior and exterior angles add up to a straight angle, we can work out what the interior angle is. Say if I label that B, because it's simply going to be 180 minus the exterior angle. And using this way of thinking, you can show that all the interior angles of a triangle, say, will add up to 180. This is a common result that we use all the time. And even if it's not a regular triangle, like an equilateral, basically. So that's a little something you might want to try yourself and show, why that would be the case using these interior and exterior angles, even though if you're looking for a general triangle, they won't necessarily be the same, but they don't have to be in order to show that result. It might be, yeah, it'd be a good little challenge to try that. So here's a typical kind of problem you might get on this, where that can often be challenging because you can't see the whole shape. So suppose we have a situation where we only have the interior angle of an unknown regular polygon. How can we determine the number of sides this polygon has? So we have something like this, where all we can see is this one point. We can't see how many sides it is. We've just got this information that the interior angle is 156. How could we find out the number of sides this polygon has? Well, first of all, we can calculate the exterior angle. It's going to be just 180 minus the 156 gets us 24. So we have an exterior angle of 24, but we know that that exterior angle multiplied by the number of sides equals 360. So the number of sides essentially times by that angle 24, will get us 360. So that's the relationship we need to be aware of, it then allows us to go from an interior angle or an exterior angle to the number of sides. Or given the number of sides, we can find the interior and exterior angles. We can go either way. And so here we can find n equals 15. So obviously that should always come out to an integer because you can't have like a fractional number of sides. So if it doesn't, then something's gone wrong somewhere. We can see this is for a 15-sided shape. So Let's move on to circles. So we've only looked at shapes with just straight sides. Now we're looking at curved shapes, circle being the simplest one. So there's a bunch of keywords we need to be familiar with when it comes to a circle. Um, First of all, circle's not a polygon. Remember, a polygon is just made up of sides. That's simply what a polygon is. If it's got one curved side, uh, then it's not a polygon. And obviously a circle is just one continuous curved side, isn't it? A circle is all the points some distance away from another point. So that point, say, in the center, the circle is then what we would call the locus of all points that are this some constant distance away. And that distance is what's known as the radius. So here we're going through some definitions now. So the radius is this distance. But if we want, say, all the points that are just this constant distance away, you can see it's kind of like a circle if I rotate that round. If you don't know what that, what quite that means, like the locus of points, we're going to be looking at that much later in our work on geometry, what a locus is. Not a locust like the insect, no, a locus. Um, so we have first there the radius, which is the distance from the center to an edge, which is going to be the same in all directions by definition. The diameter is this, the distance from one point on the circle to another going through the center. So it's essentially going to be double the radius. We have the chord, which is the same thing, going from one point to another, but not through the center. It's like a general line going from one point to another. And then we have the circumference, which is this distance all the way around. So yeah, make sure you're familiar with these terms. Again, I'm going to be using these terms throughout our geometry lessons here: radius, diameter, chord, circumference. And you need to make sure, yeah, that you're familiar with what these words mean. Certainly, when it comes to exams, if it says calculate what is the circumference, say, you need to know what that word means in order to do that. Now, sometimes we want to look at a portion of a circle like this. Like say if I draw two radial lines like this, or two radii, basically, the plural of radius, we produce this, which is what's known as a sector. So you can imagine like this being like a pizza or a cake or something, and you know how you normally just take a slice out of it, going from the middle out to the edges. That creates a sector. A sector and a chord are related to each other, so you see that chord kind of defines the sector. You get an arc, which is this distance here, going from one point on the chord to the other, and then to those two ends of the chord going into the center. You see how it defines the sector. Um, and then the shape made from an arc and its corresponding chord is what's known as segment. So that's when I like lose that triangular bit and just leave this little slice here. Now, segment sector it's often easy to get those two confused. I know I did for years. And how I remember it is like a segment is in like the segment of an orange. If you open up an orange and you take out like a little slice, they're referred to as orange segments, aren't they? And you see it's this kind of shape here. Uh, so that's how I remember it. That one's a segment, and then sector is the other one where it's like a slice. So those are some more keywords that we need to know. Right, so now let's look on to doing some actual calculations. We've done a lot of just definitions and names and all that, which is all important. You've got to know, because the reason why things have names is because they're normally very useful, very commonly used, and that's why they get a name. Whereas you take something like a 17-sided polygon or whatever, doesn't really have a well-known name because it's kind of random. So now let's move on to perimeter. What is perimeter? So perimeter of a shape is the distance going around the outside of the shape. So we can calculate the perimeter of a shape by calculating the length of each side. So for things like regular polygons, it's relatively easy. If you know what the one side is, say for a pentagon, like a regular pentagon, we can then times that by 5 because you just got 5 lots of that side. What we generally want to work out perimeter for is more irregular shapes, like say something like this. And we might be given some information about it. And we want to work out the full distance going all the way around the outside. So first of all, we need to work out what those unknown distances are. So vertically, we've got the 11 on the left and we've got 17 on the right. Looking at the difference of those, we can infer that the other vertical distance, this one here, is going to be 6. It's 17 minus 11. Likewise, horizontally, we've got the short distance of 6 and we've got the long one of 15 on the bottom. We can then infer that the top one's going to be 9. And so we can just add all that up, and that essentially gets us our perimeter. So for straight sided shapes, it's not too bad. We can kind of we need to kind of work out, like infer what certain missing sides might be, and then just got to add it all up. And you see here we get 64 centimeters. Now, where it becomes tricky is when you have, say, curved shapes. So we have a special word for the perimeter of a circle. That's the circumference. We've already seen that. So that's this distance going all the way around a circle. And we find that equals to 2 pi r, where r is the radius and pi is an irrational number. So we've kind of touched on this before. Pi is this very special number, a very particular number, which is is defined by a circle. So it's this number here. Remember, it's this irrational number. So it has this infinite decimal expansion. We can't write it down exactly. And that's why we generally have this symbol. Sometimes we work in terms of pi rather than calculating a numerical value for that reason. So ensure you know how to find pi on your calculator. Like I can show here for a typical calculator, you see pi is down here on the bottom. You see that little pi symbol in yellow. If we want to reach that, we have to press shift here first and then press that button and it will bring up pi. So be aware that you know how to use your calculators, whatever one you have. And so one thing you might notice, so we have 2 pi r. So that's basically 2r times pi. Now 2r, 2 times the radius, you remember that was basically the diameter. So another way of writing the circumference is essentially like this, like pi d, pi times the diameter. And this is where pi was essentially first discovered and calculated. You know, early mathematicians knew there was this, that the circumference of a circle was essentially proportional to the diameter. No matter how big it was, you found the circumference and the diameter went up at the same rate. And so therefore, the circumference is equal to the diameter separated by just a constant of proportionality, like what we saw in a previous lesson about proportionality. And in this case, that constant of proportionality is pi. And these days, we've now managed to calculate pi to a very high accuracy. But that's essentially what pi is and where it comes from. It's the constant of proportionality between the circumference and the diameter of a circle. In case you've never learned where pi actually comes from, that's where it is. So perimeter, we're continuing with perimeter now. We're looking at an arc. So we can see with that full circumference, which is 2 pi r, the proof of where that comes from is, you know, a bit beyond GCSE level, and you don't need to know, you just need to know how to use it. But in the bonus material, I'll show you kind of like a visual proof of kind of where that comes from. I kind of alluded to it earlier. So we're going to use it to try and calculate the distance of an arc. So we saw when we have a sector like this, and the arc is that distance, the curved distance, and going along like this. And we need certain information, like we need that angle at the center, and we need that radius 5. So the radius allows us to calculate the circumference of the circle, and then that angle essentially allows us to determine what portion of the circle we have. So you, in case you can't like visualize it, you can see I've put in a dashed line there, so you can see the bigger circle that this slice has come from. So you need to be able to kind of visualize that. And so then the circumference around that full circle we can work out. So yeah, like I said, the angle allows us to work out what proportion of the circle we have. So the circumference is this, 2 pi r. And we've got the radius of 5 centimeters. So therefore the circumference is 10 pi centimeters. So I'm not calculating it out fully yet. I'm just leaving it in terms of pi so we can preserve accuracy. And some questions will ask you to do that, certainly on the higher papers. So you want to be comfortable working in terms of pi. So you kind of just treat it like almost like a variable, like, you know, you've got like 10x centimeters or something, except, you know, it's like 10 pi instead. So the proportion of the circle we've got 60 degrees here. So 60 out of a total of 360. So that tells us we've got 1/6 of the circle. So therefore, we need 1/6 of the circumference. So 10 pi over 6, which becomes 5 pi over 3, if we simplify the fraction. So there you go. That's it. It's simple as how we calculate an arc. We just calculate the full circle circumference, determine what portion of the circle do we have, and then take that proportion of the circumference. And we can then now work out the actual numerical value by, putting pi into our calculator and all that, and round to one decimal place. So typically we want to do it this way, so we preserve accuracy rather than rounding multiple times throughout our calculations. So there we go, 5.2 centimeters is that arc. Area. So, okay, what is area now? So let's start at the very beginning in terms of dimensions. So we have a zero-dimensional shape is essentially a point. It's not an actual shape at all. And then it's like you're taking that point and you drag it along your first dimension. That creates a line. And then it's like taking that line and you drag it through the next dimension up. And the area that sweeps out is then your two-dimensional shape. And we can extend this one further into 3 dimensions, but we're not doing that right now. We'll do that in, the next lesson. So our basic unit of area is essentially a distance unit squared. So this might be, say, like a 1 meter squared. And say if we have a shape like this and we're trying to calculate what the area is, it's basically like asking how many lots of that 1 meter squared can fit in there. So if we have a nice, neat rectangular shape like this, you might fit in perfectly like this, and we can see it's 20 meters squared. And the reason for that is because it's, 4 by 5 of those squares, 4 meters by 5 meters. And so 4 times 5 gets you your 20. So that's why that's where the very base of area unit comes from, and it's the reason why we call it meters squared. Like why we don't just call it meters to the power 2. It's meters squared because it corresponds to a square. That's where that term actually comes from. So that's all good and well when we're talking about just a square shape, a rectangular shape, something like that where it fits in perfectly. What do we do when it doesn't fit in so perfectly? So if we have something like this, we can gradually build on this basic understanding of just calculating the area of a rectangle to then calculate many other shapes. So here, if we have a right angle triangle like this, we can easily calculate that. So you see, this is essentially half of a rectangle. That rectangle, we can calculate. We know it's going to be the 7 times by 8, just like what we saw. And if we half that, it then gets us the area of our triangle, 28 meters squared. So we can work that out very intuitively, but the formula would be then the base of the triangle times by the height of the triangle, 2 perpendicular sides, the base times height divided by 2. And we find that will apply for other triangles as well. So even irregular triangle, we can calculate its area. So something like this, if we've got the appropriate distances, so we've got its length and we've got its height, again, 2 perpendicular distances, we could divide this up into 2 right angle triangles like this. And if we then, put these dashed lines in, you can see this is part of a rectangle that's being split into 2 parts. And then we're taking half of each of those parts. So it's essentially half of the overall rectangle. So the overall rectangle is going to be 15 times 8. If we half that, we get 60 meters squared. So you see, because of that, we can essentially do the same thing. Base times height divided by 2. We can only use this with the information we've got here, because we need specifically the height. Say if we had this is what we sometimes might refer to as the slant height, that wouldn't work. And hopefully that makes sense why that wouldn't work now, because of where it's basically half of this rectangle. That rectangle wouldn't be calculated by multiplying these 2 sides, would it? It has to be 2 perpendicular sides. So, okay, area of a parallelogram or rhombus. Again, with a little bit of spatial reasoning, like this is something we need to develop over this course. The ability to understand space and shapes and to be able to visualize how you can move them in your mind. Something like this. How would we calculate the area of a parallelogram? It can be quite straightforward. So we can easily see how this will work by rearranging the shape. So we can imagine just chopping it like here and moving that triangle over to the other side and fuse it back in, and you see we've basically just got a rectangle. And so the area is going to be the same. So that's the thing with a parallelogram. Even though we've slanted the shape, the area stays the same. So it's just going to be 12 times 5. Area of a trapezium. And for that previous case, so we had a parallelogram. It's going to work very similarly for a rhombus. So yeah, it'd just be the 2 sides, like base times height multiplied. The area of a trapezium, again, we can do a very similar thing. So although it can be a little bit trickier. So again, we can rearrange this shape. uh, by dividing it up like this. And if we move it over like this, you can see we split this up into what looks like a rectangle on the left, but it's actually a square. If you see it's 4 by 4, shapes are not always drawn to scale, so you want to make sure you're using the actual measurements and not just eyeballing it. That one on the side, you can see it's basically two triangles. We can see that it's going to be that rectangular shape halved again. So base times height divided by 2 will get us the area of this triangle. So you see for the square on the left, it's 4 times 4. The triangle that we've split into, it's basically going to be 5 times 4 and then divide that by 2. And if we add all that up, we get 26 meters squared. So that's in, the general case. How would we, what formula could we actually use to work this out? So say if we had something like this. So we've got the two horizontal sides, the short one and the long one, and then we have the vertical height. How do we create a formula in terms of these unknowns? Well, you might see here we've got a little formula here. It's half of A, B, H. A plus B, sorry. Half of A plus B times H. And where that comes from, well, we basically just do the same thing that we just did. And you see this distance here is going to be B minus A. Because we've got the long length is B, the short one's B. So this is A, sorry. Short one is A. And so therefore that remainder is going to be B minus A. And we work out in the same way we just did before, but more, symbolically in terms of A, B, and H. So we get A times H is that rectangular area. That triangle, got the B minus A times the H and divide by 2. And then if you expand that and rearrange and then factorize, you'll find it will come to this. So you might want to try that yourself. So there's like a little proof of where that formula actually comes from. So we've got that formula and what those A, B, and H are. Allows us to work out a trapezium or trapezoid. Area of a quadrilateral. So we've got various different types of quadrilateral. We've seen like with rhombus and parallelogram. Another one we come across is a kite. And how we calculate the area of that is through these two diagonal distances. If we multiply them together, it's similar to a rhombus in that its opposite angles are shape is similar to a rhombus in that its opposite angles are equal. So not the opposite ones like from this orientation, like top to bottom, like either side of the 10-meter length, but obviously not the long 15-meter one. Those opposite angles are not the same. However, not all the sides are equal. You see, we've got two long sides that are equal. We have two shorter sides that are equals. They come in pairs like that. And the area is then these two diagonal distances multiplied together and divide by 2. And that might be almost somewhat intuitive at this point. And if you wanted proof of why that is, you can imagine dividing this up into triangles like this. And you see with a quick rearrangement, you can see it's essentially half of the rectangle 15 by 10. So 15 times 10 divided by 2, it's completely obvious now, isn't it? It would be that. So, yeah, I'd recommend playing around with some of these shapes. You can imagine like sort of cutting some out with paper and try rearranging them, like perhaps like I've done here on this these animations. So you can just really see it, and maybe some people need to do that, like to physically move things about, and so you can then get an idea for it. Other people, you might be able to just visualize it in your head, no problem. You've just got to know, what your ability is. This is one of those things that some people, it's completely intuitive, and others it's not. So area of a polygon, we will encounter regular polygons more often than irregular ones. We can calculate the area of a regular polygon if we have its side length and a perpendicular length to its center. So say something like this for a hexagon. And we already know, well, first of all, yeah, we can divide it up into triangles like this. And we could do this for any regular polygon. So from the center, we go out to each of the vertices, and you're going to cut it up into a certain number of triangles equal to the number of sides it has. So in this case, 6 triangles. And we can calculate one of them as 5 times 6 divided by 2. So we've already seen that to calculate the triangle, base times height divided by 2. And then we've got 6 of those triangles, and they're all equal. So we do 6 times that. And that will allow us to work out the area to be 90 meters squared. So you can do that for any regular polygon. To calculate the area of an irregular polygon, we need to divide it up into pieces and use various methods to solve for it. Area of a circle. So here, like the circumference, it's just dependent on the radius, because the radius is the only thing that defines a circle, isn't it? So, and we find that formula is pi r squared. So you see that pi coming in again, and it's yeah, the proof of why that is, again, is a bit tricky to explain. I'll put that in the bonus material if you're interested in where that formula actually comes from, like roughly. Um, so yeah, area is always going to involve product of two distances, because that is what area is, isn't it? Distance times distance. Hence why we get distance squared, meters squared, centimeters squared. Here with it's basically the radius times itself. Um, Again, this formula uses the irrational number pi, so we'll usually need a calculator for these kinds of problems. Area of a sector, we can do very similar thing to what we did with an arc. Just calculate the area of a full circle. So we need the angle and the radius again, because the radius allows us to work out the area. The angle allows us to work out what proportion of that circle we have. So what we do, the angle, okay, so yeah, that's explaining all that right there. So first of all, area of the circle is pi r squared. So that's basically pi times 4.1 squared. And so we work that out as 16.81 pi centimeters squared. So I'm leaving it in terms of pi again to preserve accuracy. The proportion of the circle we have is 117 out of a total of 360. So 13 over 40 is the proportion if we simplify that. But generally, you're going to plug all this into a calculator anyway, so it's not that big a deal. So we do 13 over 40 of that full area of the area of the full circle, and it'll give us the area of the sector like this. Now, we could go one step further and say if we wanted to find the area of that segment specifically. So we've got the area of the sector, which is here. The area of that segment is basically the area of that sector minus that triangular area. So we need to be able to work out the area of that triangular area, which is not something we can really do right now with just this information. This will require some trigonometry knowledge. If you're familiar with trigonometry, you might see this would be 4.1 squared, divide by 2, and then times that by the sine of the angle 117. If none of that makes any sense, don't worry, we're going to be going over it when we do trigonometry later. But you'd have to calculate the area of that triangle and then subtract it from the sector. So the segment area is going to just be this, and we can calculate it to be 9.7 centimeters squared in this case. So there you go, segment. Now, one final problem we'll look at. So this would be more example of an actual problem you might get in an exam, where it's asking us to work on many different skills at once. So imagine we've got a shape like this, and it's like this is representing a garden and with a little pond in it, and we've been given these various distances that have been measured. The council's creating this park with a circular pond, and suppose the seed costs £1.20 for every 10 square meters. How much will it cost to sow grass for the entire park? So not a particularly big park, just a little one here. You see, we can infer some of those distances there. So from the vertical, we have 21 on the right is the full distance. We see there's two shorter ones on the left, 9 and 7. So that leaves a remainder of 5 in the middle. Horizontally, we've got 15 in total, but there's 9 across the top, tells us that then there's 6 left over in that little triangular area. So we need some of those distances first. Now we can start trying to calculate the area of this whole shape, the whole grassy area. So first of all, we've got that big rectangular area on the right is going to be just 9 times 21. Then we've got the small rectangular area in the bottom left is going to be 7 times 6. Then we've got that little triangular area is going to be 6 times 5 divided by 2. And then finally, we have to subtract the area of that circle, because that's the pond, and we're not going to put grass over the pond, are we? So that is going to be pi r squared, where the radius is 6, so pi times 6 squared. So we've got, you see how we can take this big irregular shape, and then using all these different things we've learned, we can then work out what that irregular shape is going to be. This funny shape with a circle cut out of it. So we can work all those out individually, bring it all together, and you get 132.90 meters squared. So if we have it costs us £1.20 for every 10 meters of squared. We can essentially, okay, divide this by 10 meters squared, and in time, that'll tell us how many lots of £1.20 it's going to cost us. So, uh, or do the 1.2 divided by 10, which is 0.12. This would be something we have to plug in the calculator, and it gets us £15.95. So we can work out how much that's going to cost, even for an irregular shape like this. So, lot we've learned there today. Lots and lots of stuff. A good foundation to geometry there. So let me leave you with this. Did you know hexagon has many useful properties? You might have seen it in various cases in nature or in buildings and things like that. The reason why they appear in many different places is because they get the right balance between efficiency and strength. Like say something like this: if you have a rectangle and you're trying to not rectangle, you have a hexagon, you're stacking it with other hexagons. You see there how it can slot together perfectly. And we learned about pressure before. You see how this can balance pressure in all directions, like both horizontally and vertically. Whereas you take other shapes, like say a square or a circle, the circle is no good because if you start to tessellate it like this, it or try to at least, it doesn't work, and you're leaving all this wasted space in between. The square slots together perfectly, but all the pressure is acting, either horizontally or vertically. We haven't. It's not so well spread out, and so hexagon seems to find that perfect balance, and that's why you see it in nature, like things like honeycombs for bees, and we use it in manufacturing to create things like this, like nanotubes and uh, that tend to like carbon fiber, which is very, very light, but also very, very strong at the same time. We're taking advantage of the properties of this shape. So even just very basic geometry at play here. So there you go. I hope you found that interesting. Here are our takeaways for today's lesson. Next time, we're going to take out a step and we're going to be looking at three-dimensional shapes, which can be a bit trickier. So tune in for that. I will see you next time.